Hello, physicsy people. We are going to do some more work with sound today. We should have already done the lab from yesterday, and this is going to kind of tie into that. And we'll roll from there. So this is 12.2 in the book. You do have an online copy of the book, and as always, I'm here if you want to come up and get a hard copy of the book. We've got enough that you can borrow a hard copy of the book. But anyway, we'll roll with sound. 12.2. Intensity is an important idea for sound, right? So it affects how loud we're going to get this, right? So with light, right, that would be how bright the light is. With sound, we could view that more as a how loud is the sound, right? So the decibel thing, right? The power of the sound. You can physically move stuff with sound. You can do work with it and stuff, right? And the distance is a squared factor here. So kind of like same thing with gravity. Distance is important there. And as is the power, but the distance is a squared factor. So how loud is it at the source, and then how far are you away from it? That's going to both affect how loud the sound is when you perceive it. Right? So the units there are watts per meter squared. So watts is power, and then meters, since that's a squared factor, you're going to have watts per meter squared. This is an equation you should write down. So intensity is power over 4 pi r squared. Right, and we'll move that. We'll move forward from there. So that you should have seen that yesterday, right? That the intensity of the light or the area that the light covered was a squared factor, right? So the further you got away from it, the radius got bigger linearly. Linearly. Okay. So we'll go with that. So the radius got bigger as a linear function, but since the area that light's covering is a pi r squared kind of thing, then the intensity drops pretty dramatically, right? So let's view that from a different direction. Let's view that conceptually, right? We're going to build a butter gun. What's a butter gun, you ask? Well, it's a butter gun, not like this, right? So a butter gun is not a gun made out of butter, right? We're going to design a gun that can shoot butter. Right, so not a gun made out of butter. Right? I really like this picture, right? So instead, it's going to be a gun that shoots butter, right? So you put the butter into the gun, and it's going to melt. Let me move this over here, right? So it's going to melt 1 ounce of melted butter in a square pattern, right? So you're going to put the butter in, it's going to melt, and it's going to shoot that 1 pat of butter, 1 ounce of butter, evenly over the toast if you're 1 foot away. So if we go 2 feet away, how many pieces of toast could we butter at once? I'm going to Dora the Explorer thing and stare. How many pieces of toast could we butter at once? 4. That's right. You could do it 4 feet away, or not 4 feet away, 4 pieces of toast, right? It would be 4 pieces of toast. Because if you move 2 feet away, you're going to go twice as much in the up and down and twice as much in the side to side. So you would butter 4 pieces of toast at once. But how much butter would be on each piece of toast? Right? It can shoot 1 ounce of butter. 1/4 of an ounce. That's right. Is this getting awkward yet when I just sit here and stare at you? I remember when my kids were little, I would watch Dora the Explorer, and Dora would ask a question and stare at you. I'm hoping it makes you say words out loud. So this is interactive, only I can't hear you, so it's not really interactive, right? So anyway, if it goes twice as high in the up and down and twice as wide in the side to side, now you can get 4 pieces of toast, but each one's only going to get 1/4 of a pat of butter on it, right? So you have to shoot it 4 times. So your intensity is 1/4 of what it was before. Let's go crazy. Let's go 3 feet away. If you're 3 feet away, how many pieces of toast could you butter? Right? That's 9 pieces of toast because you're going to go 3 feet away. So it's going to go 3 pieces of toast high, 3 pieces of toast wide. Hey, it's a squared kind of thing that we saw before. But how much butter would be on each piece of toast? 1/9 of a pat of butter. That's right. So the intensity of the butter is an inverse square law kind of thing, right? There's an inverse. So if you're 3 feet away, you go 1/3 squared. That's how much butter is on each piece of toast. So that is really the same kind of thing as way back here, right? Same kind of thing as I love pointing with my hands, like you can see. right? So it's the same kind of thing right here. The power, that's like how much butter there was, divided by the radius squared. So, that's kind of a way of doing the butter there, right? The distance you are, or the distance you are from the toast squared. So if you're 3 pieces or 3 feet away, that's 1/3 squared kind of thing, right? So the power of the sound divided by 4 pi times the distance you are from that sound squared. So it gets weaker with a squared factor, right? Just like we see here. So don't need to write these down. I don't know what all you're writing down and stuff, but this is just some kind of examples. We had already gone through the decibels. Well, this is what that matches up with. So 1 times 10 to the third watts per meter squared. So that starts to get pretty bad. 1,000 watts per meter squared if you're close to the back end of a jet, which does damage to hearing. I know, like, my dad worked on jets in Vietnam, and he can barely hear. Like, he does not hear things at all, and he hasn't since a long time ago, right? So he's got hearing aids and all that kind of stuff. So don't climb around or don't mess with jet engines and all that kind of stuff without good hearing protection. Even with hearing protection, it can cause damage, right? But 40 decibels is like a mosquito and leaves rustling, right? You can read. Good grief. So cool stuff you can do with it. You already saw the video, right, with the levitation. If you didn't already watch that video, that's pretty cool. Where moving stuff around with sound, you can get the beads to levitate in the nodes there, right? So you have a peak here where there's high pressure, and then there's low pressure, and then high pressure, and then low pressure. And so the water will sit in those peaks. You should have already watched that. Some other stuff you can do with that is natural frequencies. So a natural frequency is like when you're swinging, right? When you're swinging on a swing, how do you pump your legs? So when you get to the top of the swing, you throw yourself back. When you get to the bottom of the swing, or when you get to the front side of the swing, you throw yourself forward. That's natural frequency. If you do that, every time you go a little bit higher. Every time you go a little bit higher. If you swing something opposite to that, you won't swing higher every time. You'll get off rhythm as you do that. My daughter had a very hard time learning how to swing. And she would pump opposite because she would get confused about what she was supposed to do. And so she would pump opposite, and she would mess herself up swinging all the time. I don't know how she couldn't figure it out, but she just couldn't figure it out. But she's really pretty and smart, so things will work out for her. But she can't swing or throw a ball to save her life, right? But Grace looked at that, right, with her video that she did for the first semester project. She looked at natural frequencies and tried to break a glass with her voice and all that kind of stuff. That was all natural frequency stuff. So the swing set example we already talked about. There was a Comaneros bridge that fell because the size of the bridge happened to be such that the wind going past it would hit the bridge at a natural frequency. And they didn't know that until they built the bridge. And so I'll post a link to that. We normally watch that together and talk about it and stuff. But basically what's happening is every time the wind would hit the bridge, it would go into that natural frequency, and it would get bigger and bigger and bigger every time. And the bridge collapsed because of that. So that was a Comaneros bridge a long time ago. Now they try not to build bridges like that. So that's it for sound. We'll maybe do another activity or two. I can't think if there's any more like demo type things that I have to see. But anyway, that's about sound. We'll do a daily quiz, and then maybe we'll work a few problems out of the book and that kind of stuff tomorrow, and then probably take a little bit bigger quiz. Not as big as a simple harmonic motion quiz, but like maybe a 12, 15 question quiz there later on this week or something like that. Anyway, hope you're staying safe and social distancing. Don't get together and hang out with each other. Then you're going to spread junk around and all that kind of stuff. So stay away from each other and just Google Meet and talk to each other.